noting, I've updated handouts 12 and handouts 13 on Canvas. These are the first time that we're using these lecture notes, so inevitably there might be a few mistakes, and we'll correct them and re-upload the notes along the way. So in handout 12, and this isn't the updated version, but in the updated version, there shouldn't be a minus p here. This should go to xk. And so the correction in handout 12 was simply to take away this minus p. And that'll be important for your homework number 4. And then for handout 13, the Kalman filter, we'll get into what I corrected later on. And I'll mention which equations are corrected when we get to them. All right, so before we start the lecture, I wanted to announce here in class, as we did on Canvas to make sure everyone received it, that we did extend homework 4. And so we gave out homework 4 last Friday. It was supposed to, or is originally due 2 days from now, but what we did is we extended that 1 week, so it's now due March 4th. And concretely, there's going to be this period of time when you have both homework 4 and homework 5 out. And we just want to give you that extra time so that you can work on these at your own pace. All right? Any questions on the schedule? All right. So last we left off with the Kalman filter, we were talking about the intuition, and we arrived at this final take-home slide where we said, because we have these 2 equations that tell us information about the kinematics, about the xk's, we should have an equation which uses the information from both of these equations to decode. And so instead of using only the neural data to decode kinematics, i.e. this equation right here, we said that now, because the previously decoded kinematics, xk, contain information about the next kinematics, xk plus 1, then we should take this into account. And it turns out that our decoding equation will now be of the form x hat k equals m1 times xk minus 1. This is the information from your previously decoded kinematics, plus some information from your neural data. And that's just m2 times yk. All right? And then we said that the Kalman filter is a way for us to recursively calculate these M1 and M2 matrices. So these M1 and M2 matrices are eventually just going to be a function of these A, C, W, and Q, those 4 parameters in the linear dynamical system. And where we stopped, we were just about to get into the derivation of the Kalman filter. All right? Or not the derivation, sorry, the solution of the Kalman filter. And then we would check to make sure that the solution makes sense. All right? So any questions before on just this brief review of the intuition behind the Kalman filter? Great. So the setup for how we fit a Kalman filter is that we basically want to find an estimator. This estimator is given by this term x hat k given 1 to k is equal to the expected value of xk given all of my neural data from y1 to yk. Now, this is a complicated looking equation. And what it basically means is if in one dimension, let's just say this xk represents the x velocity of the cursor. What I want to do is at time k, I want to build a distribution for what this x velocity is. And that distribution, it turns out, will be Gaussian because we chose our noise to be Gaussian and our system is linear. And let's say that our distribution looks something like this. And so the Kalman filter is inherently probabilistic. It won't tell you at every single point in time exactly what the value of the x velocity is, but it'll tell you, I know what the distribution of the x velocity is, and that'll give you even more information to make a selection. So the expected value here of xk given y1 to yk means build a distribution of what my vx, my xk, looks like at time k, given all of the neural data, all of my observations from time 1 to time k. And then I want to take the expected value of this x, and I'll treat that as my decoded velocity. So what's the expected value of this Gaussian distribution here? peak, yeah. The expected value is just the mean of the distribution. So when you see this expectation of just a variable x, it just means the mean of x. And so here we would decode that this is x hat k given k. And for the rest of the lecture, I'm just going to omit this one colon, just because it'll be the same for everything, and it'll be a pain to write it every single time. And so this value right here of xk, let's say it corresponds to 5 centimeters per second, would be the expected value of this distribution. So the Kalman filter would tell me the distribution of the velocity here, given my neural data. I would take the mean of that distribution and say, OK, that's my decoded velocity. Furthermore, when we have this distribution of what the velocity should be, given the neural data, we can also know how reliable our estimator is. And so this is this term, sigma squared, equals the variance of xk given all my neural data. And so concretely, this variance here corresponds to the standard deviation. How wide is my Gaussian? Sigma of k given k. And why this matters is because let's say I had a distribution for x of k that actually looked something like this. Right? It was very wide, and it had the same mean. If I were to decode my kinematics, the vx's, given this distribution, I might pick a mean that's very close to this blue line, but I would know from the Kalman filter that this is actually not a very reliable estimate because this distribution is very wide. And the Kalman filter is actually very unsure of what my velocity should be. And so the Kalman filter approach concretely is to write the distribution of these x of k's given y1 to yk's. Again, this distribution that we just drawn up here. And it turns out to be multivariate for the Kalman filter, as we discussed, because we have covariance matrices. The noise is multidimensional. And all we'll do is after we build this distribution, we're going to take its expected value, find its mean, and that'll be my decoded velocity. And then where this variance comes up is it helps to calculate the distribution at the next time step. All right, and so in general, it's very hard to write these distributions. But again, because we are using these approximations, which is that the noise, the w's, and the q's are Gaussian, or are normal. And because the system is a linear dynamical system, because those a's and those c's are linear matrix multiplies, it turns out that then the distribution of these will all be Gaussian. And you don't have to know why this is. I'm just saying it to you so that you understand. All we have to do is find a Gaussian distribution at every time step. And again, if you're interested in more detail, the derivation is on Canvas. Any questions on just the general approach of how the Kalman filter is working behind the scenes? All right. So one final note before we just show you the solution of the Kalman filter is that in high dimensions, we care about covariance matrices instead of scalar variances. And so we're going to turn all these sigma squareds, which are just the scalar variance of the xk, into these covariance matrices, which are the covariance of each of the dimensions of xk. And for the rest of this lecture, we can just assume a simple case where the sigma k's, given the neural data up from y1 to yk, is a diagonal matrix, right? So let's say that here we have, let's say it's a 3 by 3 matrix where dimension 1 is vx at time k, dimension 2 is vy at time k, and dimension 3 is z velocity at time k. Then the diagonal terms here would be the variance of vx at time k, given the data up to time k. The variance here would be the variance of vy at time k, and here the variance of vz at time k. And then the rest of these terms will be 0. All right? So this is exactly what we talked about in the last lecture about what these covariance matrices define. And so this will just be the variance along each dimension. Okay. All right, so this is the Kalman filter solution. And what I want to do is I just want to go through one while loop of this recursion just to ensure you all that you can actually calculate this thing. And so the solution I'm just posting here. Again, the actual derivation is a 2-page handout on Canvas. And so what we'll do is first we're going to initialize everything. And so at the very first time point, we're just going to say that our distribution has mass 1 at 0. So we start off with a mean of 0. And the covariance of this is also equal to 0. So that's just some initial state. It turns out that if you pick an initial state, which is closer to your steady state value that we eventually converge to later on, then you can make this convergence occur quicker. But as we mentioned before, for neural prostheses, these things will converge on the order of seconds. And so we don't really care too much about the initialization. So we'll just make it 0 to be simple. And what we're going to do is we're going to recursively calculate until the convergence of kk. And so this will literally be, in MATLAB, a while, and then something that looks like, well, we'll tell you exactly what it is on homework 5, but it would look like while k plus 1 minus kk is greater than some epsilon tolerance, right? So while this k's have not converged, then I'm going to calculate these 3 equations recursively. And so very concretely, if we go in here and we set k equals 1 for the first time bin, we would say that sigma 1 given 0, which is sigma 1 given 0 is equal to A sigma 0 given 0, A transpose plus W. And we know what sigma 0, 0 is. Sigma 0, 0 is just equal to 0. And so this term would cancel out. And we would have that sigma 1, 0 is equal to W. At that point, we've calculated sigma of 1 given 0. And then we would proceed to the next equation. So in this equation, we would literally write out sigma of 1 given 1 is equal to sigma of 1 given 0 minus sigma of 1 given 0, C transpose, C sigma 1 given 0, C transpose, plus Q to the minus 1, C sigma 1 given 0. And the point of writing all of this out is just to see that sigma 1 given 1, the next term that we want to compute, is merely a function of these C matrices and these Q matrices, which we know from our linear dynamical system, right? Those are the actual, this is the matrix that maps the x's to the y's, and the Q is the covariance of the noise in that equation. And then all these sigma 1s given 0s, we've just calculated here. And so we can calculate this term, sigma 1, 1 exactly. And then after that, we can also calculate this term kk exactly. So k of 1 would equal sigma of 1 given 0, C transpose, C sigma 1 given 0, C transpose plus Q minus 1. And so again, k1 would be ambiguous to calculate. And then we would start the loop over again. And then we would calculate sigma 2 given 1. And this would be a function of sigma 1 given 1, which we calculated on our previous loop. All right? So this should be very easy to implement in MATLAB. You just write out these 3 equations, and you iterate through them again and again. Anjali?
I'm sorry, what does sigma 0 given 1 colon 0 mean?
So I put that in there for notation, because when we initialize this loop at k equals 1, then this first term is going to be this term here. This will be sigma 1 given 1 to 0 is equal to A times sigma of k equals 1, sigma of 0 from 1 to 0. And so I just wanted to make it clear, since that this thing doesn't exactly look like sigma 0, 0, this thing here is this term here. Is that clear to everyone? So it's just to make sure that you can initialize this entire equation. So just for the first iteration when k equals 1, this term here is equal to 0.
Thank you.
All right? All right. And so I know that this isn't very insightful, but just want to go through it to make sure that you guys are all comfortable on how to actually write this while loop on homework number 5 to calculate all your terms. And so eventually, this while loop will converge. And we'll call the converged values of these sigmas and these k's sigma infinity and k infinity. All right? And then for terminology, in case you start talking to your friends who are also doing Kalman filters, this k at time k is called the Kalman gain. And so if someone is saying, what's the Kalman gain of your system, you know exactly what term they're referring to. It's this term here. And we'll talk a bit about what this Kalman gain actually means in a few slides. All right, so after you perform this recursion, you achieve a sigma infinity and a k infinity. And the solutions for M1 and M2 are then given by these matrix operations. So M1 is equal to A minus k infinity C times A, and M2 is equal to k infinity. And if we know M1 and M2, then we can begin to decode, because now we have incoming new neural data yk. We started off with x hat of 0 equals 0. That's how we initialized our system. And so when we have our first neural data at y1, then we can calculate an x hat of 1. This term will just be 0. And then given x hat of 1, when neural data comes in at time 2, we'll be able to calculate x hat of 2, and so on and so forth. All right? Is that all clear to everyone? Anyone have any specific questions on this? Nathan?
So is the sigma infinity, we're not using it here. Is it just used for, I guess, guiding the convergence in the derivation of the Kalman filter?
Yeah, so the sigma infinity is basically changing this k infinity parameter. So this k infinity, and we'll talk about this a bit more in the next slides, is basically weighting your neural data. So the neural data here is equal to, is being multiplied by this matrix M2, and M2 is just k infinity. And so that sigma, if it's large for, that sigma, if it was equal to, say, 100, 1, and 50, would modulate the parameters of this k infinity. And I'll talk more precisely about how that is 2 or 3 slides from now. But it'll basically be a way for us to weight these dimensions. And so if sigma of your velocity term in the x direction was very large, then I would want to downweight dimensions, or I would want to downweight dimensions that are calculating that velocity. And so again, we'll get to this. We'll get to this in a few slides. And the sigma will basically carry through the uncertainty and allow this k infinity to be modulated. All right, before I go on, I also wanted to really briefly note that we're showing you this equation for the Kalman filter, and you probably won't see this anywhere else. And so usually the way that people write Kalman filters is to plug in this M1 and this M2 here, and it ends up looking something like this. So it'll look like x hat k is equal to A x hat k minus 1 plus k times yk minus c a x hat k minus 1. And so if someone comes to you and they say, this isn't a Kalman filter, this is a Kalman filter, well, they're mathematically equivalent. The reason that most people write it this way is because it's somewhat intuitive as well. And so again, you won't be required to know this for the final, but I just want to share this intuition in case you work with Kalman filters in the future. What this equation is saying is that xk is first the dynamical update of a x hat k minus 1. And so this is nothing but that equation xk equals axk plus noise. All right, so first we're going to just update x hat k by our dynamical model. And then what you can think of is that this term here is a correction term. It's an error correcting term. And how can we see that? Well, first we see that a times x hat k minus 1 is our estimate of the next decoded state absent of neural data. And so this is akin to x hat k minus 1, but, x hat of k. But before we've seen any neural data. And so this given yk minus 1 is saying that we've only seen up to time yk minus 1. And then we'll remember that there's a second equation here, which is saying that yk is equal to cxk plus qk. And so now this term c times x hat k given k minus 1 is sort of like a predicted neural data. So based off of my dynamical model alone of these two equations, I can multiply x hat k minus 1 by a to get xk, then multiply that by c to get a predicted neural data. That's y tilde of k. And then what the Kalman filter is now saying is, I'm giving you the true neural data. I observe at time k what the true neural data should be. And so this yk minus tilde yk is sort of like my error in predicting the neural signal. And so this whole term here becomes an epsilon in the neural signal. And this is called the innovation, if you ever hear of it. And this thing is multiplied by the Kalman gain. So the Kalman gain corrects your state estimate as a result of just propagating along the dynamics matrix by multiplying your error in predicting the neural data. And so that's another intuition behind the Kalman filter. But for this class, you will only be required to know this simple equation that is a vote between your previous kinematics and the neural data. Any questions on that? All right. So now we want to ask, does the Kalman filter solution make sense? And because the equation was pretty complex with matrix inverses, we're going to just turn everything into scalars, because all of us know how to invert scalars in our heads, but we can't invert matrices. And so I'm going to turn that big matrix A into a scalar A. I'm going to turn the big matrix C into a scalar C. I'm going to make our noise terms just single numbers. And so they'll be one-dimensional Gaussians that are still zero mean, but have some variance given by these terms here. And what I can do is I could take that complicated equation for kk and just write it by replacing all the sigmas, right, with sigma squareds, the big matrices with C of C with little c. And then matrix inverses just become divisions, right? Because if you have A times A negative 1, and this equals the identity, the scalar analog is that A times 1 over A equals 1. And so all I've done is I've replaced these terms accordingly in the Kalman gain and arrived at this equation, right? And so I've written everything here in terms of scalars. And let's just start to see if the Kalman filter makes sense. And so in the first experiment, what we're going to do is we're going to take the sigma q squared term, which is the noise in the observation process, and we're going to turn it up to infinity. And so if I turn this up to infinity, what should my state estimate, x hat of k, be? If you were just using common sense, looking at these two equations, and this noise was infinite, what should I do, or what should the Kalman filter do if it was working? Yeah, so Nathan said not use any of it. So because this qk is infinite, then this means that this equation here is infinitely unreliable, right? And so if that equation is infinitely unreliable, then I would always just want to use this equation, which even though it's still noisy, at least is a bit reliable. And so if this qk went to infinity, this equation would be meaningless. It would be as if we never had it. And so we would expect that x hat k would equal a times x hat k minus 1. Does that make sense to everyone? All right, so if I turn up sigma q squared to infinity, right, I'll notice that kk here would go to 0. And that's just because sigma q squared, as you all see, is in the denominator. This is infinite. So any number divided by infinity is equal to 0. Therefore, m2, since this kk has now gone to 0, will go to 0. And so if m2 goes to 0, and our equation was x hat k equals m1 xk, minus 1 plus m2 yk, then this term, m2 goes to 0, so we would now ignore this. And then m1 here is equal to a minus c-a-k-k. Again, I've just replaced all the matrix with scalars. And if kk is equal to 0, then we see that this whole term goes to 0, and m1 is just equal to a. All right? And so this turns into an a. And we see the Kalman filter does exactly as we would expect. We turned up the noise on this equation to infinity, and it ended up decoding x hat k is equal to a times x hat k minus 1. All good, right? And so now let's do the opposite. Let's turn this noise down to 0 so that this equation is perfect. Then what would the equation for x hat k be? So we'll do this in purple. So intuitively, if this equation was perfect, would I want to use this equation at all? Right? This equation provides additional information, but that information is noisy. And I already have a perfect equation. So if I have a perfect equation, why would I use a noisy equation? And so if this qk is equal to 0, then I could take away this term. And I would have a perfect equation for my kinematics, right? Which is just that x hat k is equal to 1 over c times yk. Does that make sense to everyone? All right. And so now our goal is to see, does the Kalman filter arrive at the solution if we turn this noise to 0? All right. So if sigma q squared equals 0, then in our expression for kk, this would go away. And we would just get that kk is the ratio of these two terms. These sigma squareds are equal, so they cancel out. And then one of these c's cancels out with these c squareds. And so we would get that kk equals 1 over c if sigma q squared was 0. And so if kk is equal to 1 over c, then m2 here is equal to 1 over c. And m1 is equal to a minus c times a times 1 over c. The c and the 1 over c cancel. The a's cancel to give 0. All right? And so if sigma q squared equals 0, if we take away this noise, then kk is equal to 1 over c. And this is the scalar analog of performing the inverse. 1 over c is the same as performing the pseudo-inverse c dagger. Okay? And so this means that the state update process is ignored because the m1 term will go to 0. All right? Is that clear to everyone? Does anyone want me to go over any part of this slide again? All right, the take-home message from this should be the Kalman filter for all the equations that we showed looks like it's doing the correct thing. Right? When I turn up the noise on this, it'll ignore it. And if I set the noise to 0, it'll use it exclusively. All right. Very quickly, I just want to do the same for the state terms. And so since we've seen this already, we can go through this more quickly. If we turn up the state noise, this w, to infinity, then this equation becomes infinitely unreliable, and we should only use the observation process. So if sigma w squared goes to infinity, then kk becomes 1 over c. This one's actually a bit harder because it requires you to know the equation. Anjali?
Because sigma squared k is the variance of xk, which has the term added.
Exactly. There's this term sigma squared is hiding a plus sigma w squared. And so if sigma w squared is going to infinity, then these two terms will dominate, and sigma q squared will become relatively insignificant. And so because these two terms are dominating, then again, we'll have that the sigma squared and the sigma squared will cancel out. Right? This would more formally be the limit as sigma k given k minus 1 squared goes to infinity of kk. And so in that limit, we could cancel out these two sigma squareds, and we would just get, again, 1 over c. And then that 1 over c is the same as what we saw before. When kk is equal to 1 over c, m1 will become 0. and this M2 matrix will become 1 over C. And so then we would get that because x hat of k equals M1 x k minus 1 plus M2 yk, this would give us M1 equals 0. It would give us x hat of k equals 1 over C yk. Okay? And then if sigma w squared equals 0, because we initialized our variance to be 0, it turns out that all these terms, sigma squared k given 1 to k minus 1, will all equal 0. And if this numerator is 0 and this denominator is non-zero, then kk will equal 0. And again, this will mean that we ignore the observation process because sigma squared w going to 0 means that this is a perfect equation, and we should always follow this equation to decode. All right, so the Kalman filter appears to be doing exactly what we would expect. And a side note is that when the noise is multidimensional, the Kalman filter will also downweight neurons that are modeled to have a lot of noise. And so this is a natural way for the data to speak for itself. And so instead of having to go in and say, OK, you're a neuron with a lot of variance. I don't want your weight to be that high. I'm going to manually do some deweighting. What we'll have here is if our Q matrix is equal to 100, 1, and 50, that means that the contribution of neuron 1 to the kinematics is really noisy, right? It's lousy, it's 100. And dimension 2, though, is pretty good. It only has a noise variance of 1. And dimension 3 is OK, it's moderate. It has a noise variance of 50. And so if I were to, I wrote this as a diagonal matrix because I can invert that. If I were to calculate Q negative 1, that would equal 1 over 100, 1, and 1 over 50. Zeros everywhere else. And you can see that this term Q negative 1 appears in this Kalman gain. And so, so let's just ignore this term for now. This term will affect this inverse. But if this term C sigma C transpose wasn't there, then we would be multiplying this by Q negative 1. And that would really downweight the first dimension. It would upweight relatively the second dimension, and it would downweight the third dimension. All right, so whenever you see these negative 1s, you can think about this as like a dividing by these matrices, even though we don't actually do that because that's not a legal operation. It's something that you can use as intuition to see that if you do have these large values of noise, those dimensions are going to be downweighted. Is that all clear to everyone? All right. OK, so now we're going to come up to see the big picture. We'll start off with a linear dynamical system with parameters A, C, W, and Q. For this linear dynamical system, what we want to do is we want to estimate the state at time k, denoted x hat of k. We've said that this is a linear combination of the previous kinematics and the neural data. We calculate how we combine those two sources of information by using the Kalman filter recursion. And these are the two equations we ultimately get out. And then we can decode new incoming neural data by simply calculating this equation and propagating it through time. All right? So if I stopped here, would you guys be able to fit a Kalman filter today? Are we missing anything? If I just gave you neural data, the same R struct that you have in homework 4, and it has cursor positions and neural data, have I omitted anything here that would let you solve the Kalman filter? Sorry, what was that? Variances, yeah. So that's getting along the correct question, the correct answer, which is I haven't told you what these A, C, W, and Q matrices are. So we don't know how to calculate those yet. And so given that you know A, C, W, and Q, you can go ahead and you can calculate the Kalman filter via the steps that we've just gone through. And so the last part of this lecture will just be to say, how do we calculate A, C, W, and Q from our neural data? And this will be the easiest part of the lecture, or the easier part of the lecture, I should say, because we've already set up the machinery to do this. And so we have these two equations, and we want to know how to find the parameters A, C, and then the covariance matrices of these noise terms W and Q. All right? And so the first thing that we want to note is that because WK and QK are zero mean noise terms, we can ignore them in the average when we do our regression. Okay? What do I mean by this? So let's say that I want to fit a scalar parameter A that relates x of k. Let's just call this the velocity in the x direction at time k to the velocity in the x direction at time k plus 1. And what I have are a bunch of data points, which I'll just draw in purple, like so. If I wanted to fit the best scalar A, I would simply draw a line through these cloud of points that looked like this, that fit the data pretty well. All right? Now, there's noise that corrupts this equation, but the noise is zero mean. And so if the noise had a mean of 1, then on average, these points would all move up by 1 unit. But because the noise has zero mean, it'll change these purple points, but on the average, the purple points will not have moved. Sorry, I'm redrawing them as blue points. The blue points will not have deviated from this line unequally. And so they may have greater variance. They may look like this, but they should still be centered around the screen line, because on the average, I didn't shift the mean at all. Is that all clear to everyone? All right. So because these WKs and these QKs are zero mean noise terms, they actually don't affect this regression at all. And so what we can do is we can throw away these Ws and these Qs for fitting just A and C. And that leaves us with these two equations. And we know how to solve this using our techniques from the optimal linear estimator. And so for concretely for these equations, what we would do is we would write x2 x2, x3, all the way up to xk, right, is equal to a times x1, x2, all the way up to xk minus 1. Is that all clear to everyone? This is just simple matrix multiplication. So x2 is equal to a times x1. x3 is equal to a times x2. And I'm just going to call this matrix up here will correspond to this term, and this matrix here will correspond to this term. So here I'm trying to use MATLAB notation. The colon means take all of your rows, and then to the end means take the second element, which is x2, all the way to the end, which is x of big K. And this is 1 to end minus 1. All right? And then to actually calculate A, what I would do is I would take this x of just 2 to end, and then I would invert this by taking its pseudo-inverse and bring it to the other side. Is that all clear to everyone? Does anyone want me to go through this in more detail? All right. And then the C equals yx dagger is very easy to see. This is exactly the same as the linear optimal estimator. We'll take all of our y's, concatenate them. That's the big matrix Y. Take all of our x's, concatenate them. That's this big matrix X. And so C is just equal to y times pseudo-inverse of x. Okay. All right, the last note here is that A should also obey physics. And so there are some things that we can pre-program into this A matrix. So the first is that the position should just be the integrated velocity. And you guys have been asking this 3 times, so I won't go over it again. And so because we know from physics that this has to be true, we can actually just plug it in. We don't need to fit those terms at all, because we know if we fit the terms, we might actually get something like 0.98 or 0.99, simply because the data is noisy. So we know something better than the data. We know that this equation is true here on Earth. And so, so we can program these values in. And when we are working in homework 5 with Kalman filters, what we'll really want to be fitting is how the Vx's and the vy's update through time. And so this is sort of capturing, or this is capturing the inertia of the cursor. So let's say that vxx is equal to, say, 0.9, vxy equals 0, vyx equals 0, and vyy equals 0.9 as well. So what this is saying is that part of my estimate for the next velocity is that the velocity should really be pretty close to what it was at the previous time step. So my velocity at 500 milliseconds, let's call it, was, let's say that at k equals 500 milliseconds, that v k of x was equal to 100 centimeters per second. This equation would then update to tell me that at the next time step, vk plus 1x equals 90 centimeters per second. And so this is a way in which we can capture that the velocities at adjacent time points should not be changing that much. So this term here is basically smoothing our velocities in time. Is that clear to everyone? Anjali?
Why do you need to use the common filter? Why do you need to have the positions in the kinematics vector at all? Why can't we just use the velocities in the bottom right of the matrix?
We could do that. And so the reason is, and the homework won't be a good example. Actually, maybe the homework does do this. I forget. I'll have to check. Because we may want to have an equation relating the positions to the neural data. And so it's just easier to put them all in the same vector so that we can, when we calculate the C matrix, it'll have both the velocity to neural data terms and the position to neural data terms. But you're right that for the state update equation, we could have just used this term here, capturing the inertia of the velocities, and then integrated that the position.
So are the tuning curves position variant?
The tuning curves will change over time. That's correct.
And they change with position?
Yes, I believe so. I can't actually quote the study that states that, and maybe Professor Shinoy knows, and we can talk about that after class. Yeah. Nathan?
Could you just explain how to think of vxy and vyx?
Yeah. So in general, these terms should be 0 unless in your data set the x and y positions were correlated. And so let's say you only reach to upright targets and not to down left targets. Then overall in your data set, you would have built in this probably undesirable feature that when you go up, you probably also want to go a bit to the right. And that's just because your data set was filled with all these upright reaches, but not down left reaches. And so you can always be assured that these vx's, vy's, et cetera, as is common in machine learning, are going to fit the training data that you give it. And if the training data that you give it is unbalanced, then these terms would become non-zero. But that's exactly what you told it to learn. You told it to learn the dynamics of these reaches. And it's on the data set that when I go up, I'm in general going to the right also. Okay? So that's another reason why, as you guys have seen in homework number 4, we have these 8 equally spaced targets that are uniform around the circle and have the same distances. That's to make sure that the kinematics of the reaching are all uniform. Okay. All right, and then after we find the A's and the C's, we can find the W's and the Q's. And so if we were to observe W1, W2, W3, et cetera, and they were 0 mean, then we know from statistics a formula to calculate the covariance matrix. And that is just that big W here is equal to 1 over k minus 1, the sum of, I'll call this big K, the 2 lines denote big K, little k minus 1 to big K of WK, WK transpose. And so this is just the formula for covariance. We won't expect you to know how to derive it or how to arrive at these terms like k minus 1. But the problem is that to get this, we have to have observed the noises W1, W2, et cetera. Now, we don't directly observe these noises, but because we know what A and C are, what we can do is we can back calculate what these noises are, right? So W1 is merely x2 minus AX1, and so on and so forth. Is that clear to everyone? Similarly, QK is just YK minus CXK. All I've done is I've subtracted these matrix multiplies and put them on the left-hand side of the equation. Okay? And so now I have a sample of the noise for each time step, W1, W2, all the way up to WK, and also for the observations, Q1, Q2, all the way up to QK. And I know some of you are going to check this. If you were to look at these W1s, W2s, et cetera, and you were to look at their distribution, you would find that they are not normal. And this is just to rehash the fact that when we say that these noise terms are zero, mean, and normal with some covariance matrix, that's an approximation that we're making so that we can use the Kalman filter. But if you actually were to plot out these residuals, the W1s, the W2s, et cetera, you would find that they aren't normally distributed. So it perhaps isn't the best assumption, but it turns out that when we assume more complex noise models or more complex dynamics, these parameters, these W's and these Q's, become a lot more difficult to find. And you really need some more modern machine learning to do that. All right? And so we can use this equation, and we can state that W is equal to 1 over K minus 2. There's a K minus 2 because we only have K minus 1 of these terms, right? We have from 2 to end instead of from 1 to end. And the covariance matrix has this normalizing factor 1 over K minus 1. So this becomes 1 over K minus 2. And then it just becomes all of your residuals times themselves transpose, and similarly for the Q matrix. All right, any questions on this slide? All right. All right, so now we're really going to put everything together from your starting R struct. This is how you're going to fit a Kalman filter. So first, you're going to find A, C, W, and Q. You'll first find A and C by finding your velocities in the neural data and making this matrix multiply. Similarly for C. And then the W's and Q's, you're going to calculate the residuals, which is this equation right here, and then plug it into the formula for your covariance matrices. And from this, we have A, C, W, and Q. All right. After that, we perform our Kalman filter recursion, which has A, C, W's, and Q's, and an initial value for the covariance of 0. And we'll keep calculating these three terms until convergence. Nathan?
Can you go back a slide?
Yeah.
Is this where you changed the...
Oh, yes. For the original handout 13, I did not have these normalization constants. And so make sure you download the new handout 13, which has these normalization constants correct. All right. So we'll do this recursion until we have a convergence of the Kalman gain. And then after that, we'll calculate our M1 and M2. And given that, we can then decode new neural data by calculating x hat k equals the previously decoded kinematics times M1 plus the neural data times M2. And homework number 5 will walk you through every single one of these steps in detail, and you will fit a Kalman filter from scratch. All right? Any questions on any step of the Kalman filter? Is this all clear to everyone, or is it a bit hazy? Raise your hands if it's clear. Oh, OK. I haven't done a good job then. Is there any part that people want me to go over through? Nathan?
When you wrote the W is 1 over K with the sum, is that, what W is that?
In the sum, the W's are referring to, oh no, I lost all the, oh, there, OK, yeah. These W's are referring to observations of the noise. And so if you observed noise coming into your system, and you observed noise at time 1, at time 2, at time 3, et cetera, then this equation here would take your little observations, the w's at time 1, at time 2, et cetera, and calculate the covariance just via this formula.
So is that then a matrix? It should just be a scalar, right?
So because that, so if the w was, so let's say that the xk is 5-dimensional, it's a 5x1 vector, then these w1s, w2s are also 5x1 vectors. And because they're 5x1 vectors, when I do this, this is a 5x1 vector, and then this next term here is transposed, so this is 1x5. And so this actually, this sum here becomes a 5x5 matrix. And so basically, you're just summing 5x5 matrices and then normalizing them. All right, I'll touch on one last slide. Actually, before I do that, is there any other step of the Kalman filter that people want me to go over? Yeah.
Can you go back? So when computing your A and C matrices.
Yeah. Sorry, this is not. Okay. All right.
Can you explain again why we made the simplification that our why we made the simplification without any noise?
Yeah. So, the purple points here were our original lines, and if the noise was not zero mean, so critically this noise is zero mean, and that's what allows us to make the simplification. If the noise was not zero mean, and let me plot this in yellow, let's say the noise had a mean of 1, then all these purple lines would systematically shift up here. And if I want to fit a line through them, then it would look like it was shifted up by 1. Because I have so many points k plus wk. Now, expectation is linear, and so this term here will equal expectation of a xk plus expectation of wk. And the expectation of wk is merely its mean value. And so this term here will just go to 0. And we'll get that the expected value of xk plus 1 is equal to a times the expected value of xk. And so that's another way that you can see the noise cancels out. It's past time, so I want to let you guys all leave for today. I'm happy to take extra questions up front. All right.